Welcome to the Explainer. I am so thrilled to have you here today. If you've ever looked at a math problem, seen that giant curly bracket grouping together two or three different equations and just thought, wait, what on earth is going on here? Well, you're in exactly the right place. Today, we're going to completely demystify piecewise defined functions. I know the name sounds a bit formal, but really, these are just equations with multiple formulas. And they're actually incredibly useful. They brilliantly model real-world systems where behaviors change under different conditions. I promise you, once we break them down, they are not intimidating at all. Actually, they're incredibly logical and structured. So let's get into it.
Here's our quick roadmap for today. We'll start with 1. What are piecewise functions? Then 2. Evaluating function inputs. Next, 3. Graphing piecewise functions. And finally, we'll wrap up with 4. The vertical line test.
All right, section 1. What are piecewise functions? Let's define the core concept.
Okay, let's dive right into this. A piecewise defined function is simply a function whose rule changes depending on the exact value of the input. Each piece of the function has its very own formula. And honestly, this is the secret to the whole shebang right here. Each piece is defined over a specific interval, or a specific set of input values. So rather than having just one single rule that applies to every single number forever, the rule literally changes based entirely on the specific input value you hand to it.
Now, a really helpful way to think about this is that the input restrictions act as, well, gatekeepers. When we evaluate these functions, we've got to pay super close attention to these restrictions. Think of them like a bouncer at the door of a club. Before a number is actually allowed to use a specific formula, it absolutely must pass that gatekeeper's test. If your input doesn't meet the requirement, nope, it gets turned away and has to go find the correct formula where it actually belongs.
Because we're using different formulas on different intervals, the graph you end up with at the end might look a little fragmented. You should actually expect visual discontinuities, things like holes, jumps, or complete breaks in the line. So, if you're graphing and your line suddenly stops, jumps up a few units, and starts again, don't panic. You probably haven't made a mistake. That is perfectly normal for a function whose rule suddenly changes.
Moving right along to section 2, evaluating function inputs. Let's practice the grammar before we try to write the essay.
Let's solve a little puzzle together using a function we'll call f of x. Let's say the rule is x plus 7 if x is less than 2, and the rule is just 5 if x is greater than or equal to 2. Okay, let's find f of 1. Our input here is 1. We walk up to the gatekeepers and ask, is 1 less than 2, or is it greater than or equal to 2? Well, 1 is strictly less than 2, right? So it meets the first restriction. That means we use the first formula, x plus 7. We plug in our 1, and 1 plus 7 gives us a quick result of 8. Awesome. Next puzzle. Let's find f of 3. Is 3 less than 2? No way. Is 3 greater than or equal to 2? Yes. So we use the second formula, which is simply 5. Notice there's no x to plug into here, so the result is literally just 5. The absolutely crucial takeaway here is that even though the function gives you two formulas, only one formula is ever used for any given input value.
And this brilliantly illustrates the exact same process, just with a brand new function, g of x. Let's say g of x uses the formula x squared when x is strictly greater than 0, and the formula x plus 2 when x is less than or equal to 0. All right, let's evaluate g of negative 3. Well, negative 3 is less than or equal to 0, so it passes that second gatekeeper. We use the formula x plus 2. Negative 3 plus 2 equals negative 1. Simple enough. Now let's try g of 4. 4 is greater than 0, so it meets the first restriction. We use the formula x squared. 4 squared is 16. It's incredibly systematic once you get the hang of it. The input always determines which piece of the function applies.
All right, section 3, graphing piecewise functions. Time to start building the visual. Now, before we draw a single line, we really need to isolate a super common tripping point. You are going to use open circles for excluded endpoints. That means whenever your restriction is strictly less than or strictly greater than. Contrast that directly with closed circles. You use solid, colored-in circles for included endpoints. That's when your restriction says less than or equal to, or greater than or equal to. That equal to part, that's exactly what tells you to color in that circle. This distinction is absolutely vital for making sure your graph is mathematically rock solid.
The golden rule when it comes to graphing these is to graph each piece completely separately and only then combine them. Here are the exact 5 steps we'll use to construct our final graph. Step 1. Identify the formula and the input restriction for each piece. Step 2. Graph each formula only on its specified interval. Step 3. Use those open circles for excluded endpoints. Step 4. Use closed circles for included endpoints. And finally, Step 5. Combine all the pieces into one single graph. Okay, let's actually put these steps into practice.
Here's our specific example. Let's say we want to graph a piecewise function f of x. The first piece is the formula x plus 1, but remember, this only exists for x values strictly less than 2. The second piece is the constant formula 5, and this one only exists for x values greater than or equal to 2. Let's tackle this, well, piece by piece. Starting with step 1, we graph that first piece. We're going to draw the line y equals x plus 1. But remember our gatekeeper. We only draw this line to the left of x equals 2. Imagine an invisible vertical boundary right there at x equals 2. We literally stop drawing when we hit it. Now, what happens exactly at that boundary? Well, since our rule is strictly less than 2, the number 2 itself is not included. Therefore, we place an open circle right at the coordinate point 2, 3. Why 2, 3? Well, because if we could plug 2 into x plus 1, we'd get 3. So the line goes right up to that exact spot, but we leave the circle empty to show it's not actually included. Let's move on and see how this builds with step 2. Now we graph the second piece. We need to draw the line y equals 5 for x greater than or equal to 2. This is just a flat, horizontal line. We start it exactly at x equals 2 and extend it out to the right forever. Now look closely at the restriction again, greater than or equal to 2. Since 2 is included in this interval, we place a solid, closed circle right there at the coordinate 2, 5.
And finally, step 3, we combine the pieces. Let's look at our overall canvas now. We've got an angled line coming up from the left, stopping at an open circle at 2, 3. And then, directly above that open circle, starting at a solid closed circle at 2, 5, we have a horizontal line shooting off to the right. We did it! We successfully took 2 totally separate, distinct pieces and combined them into a single, unified visual representation of our piecewise function. And hey, notice that jump between the 2 pieces? We talked earlier about how jumps are a completely normal visual discontinuity, and here it is in action, perfectly modeling a sudden, instantaneous change in the rules.
Section 4. The vertical line test. Verifying the function.
I want to leave you with this final puzzle to really ponder. Does our combined graph with its jumps and very specific open and closed circles actually represent a true, valid mathematical function? Think back to the vertical line test. If you swept a perfectly vertical line across our whole graph, what exactly happens at x equals 2, where that one piece ends and the other begins? Because we were so careful to make the bottom circle open and the top circle closed, does it pass? Think about it. What would have happened if our gatekeepers had allowed both to be closed circles? I'll let you visualize that test in your head. That right there is the beautiful, watertight logic of piecewise functions. Thank you so much for joining me on this explainer. Keep practicing, and I'll catch you next time.